Hello everyone, and welcome to the last lecture of this first part of the Ecohydrology course. We will see today is a lecture on the evapotranspiration and how it interacts with the ABL, the atmospheric boundary layer. And it's a relatively long lecture divided in three parts. The first part here deals with the combination approximation. The Penman-Monteith equation will derive it together to see what type of structure it gives rise to, because it will be useful in the last part of the class where we will put everything together and integrate at the daily level evapotranspiration. That will provide us with a reasoning behind the Priestley-Taylor approximation. And then in the central part of the lecture, the most consistent one, we'll deal with the atmospheric boundary layer dynamics. What happens when we don't know the quantities just above the canopy, so we cannot close the system, and we need extra equations. These next extra equations are the energy, the water balance, and the growth of the boundary layer equation, which form an interesting dynamical system, which provides us with the diurnal evolution of the combined Soil-Plant-Atmosphere Continuum ABL system together. So this will help us describe the whole key land-atmosphere interaction, how land processes affect the atmosphere and how the atmosphere then in turn affect the land processes. Let's get to the first part of the lecture, the combination approximation. We start with considering a wet surface so that the water potential at the surface is zero. Water is perfectly freely available to be evaporated. It's not unsaturated. So the system of equation is as follows. We have the system combination of these three equations. Let me get the cursor here. Yes. We have the evaporation rate, which is proportional to the difference in vapor pressure times the atmospheric conductance. We don't have stomates here, so there is only the atmospheric conductance. The sensible heat flux and the energy balance equation. The sensible heat flux is proportional to the gradient of temperatures, we know, proportional to the same atmospheric conductance, because we have the same pathway between the surface and the atmosphere for the two energy fluxes. The two energy fluxes are combined here by the energy equation, where the total available energy from radiation is partitioned into sensible latent heat flux related to evaporation and sensible heat flux H. How can we put those equations together? How can we get rid of the explicit surface temperature dependence that is what gives us trouble here? The equation is nonlinear, so if we don't want to solve numerically this system, what do we do? That was Penman's original question. So what we can do is to do a little bit of massaging on the evaporation equation. So let's write it again here, what we had before. And what we can do here is to make the VPD, the vapor pressure deficit, appear. So how do we do that? We add and subtract the saturated pressure at the temperature of the atmosphere. In this way, you can recognize here that we have the VPD, the vapor pressure deficit. This is simply the difference between the saturated pressure deficit and the actual pressure, vapor pressure in the atmosphere. And on this, so that's what gives us this VPD. On this side here, we have two differences of two saturated vapor pressures. So we're basically taking the difference of 2 points located on the Clausius-Clapeyron equation. And so if we look at that, that's what Penman originally did, is that if TA of the atmosphere above the surface and TA just at the surface are not too far away, we can actually linearize this equation. So instead of this difference, E naught sat and EA sat, this would be the actual value that we have in the system. We take its linearized value, meaning we take the slope at the point where we imagine that we know the temperature in the atmosphere. Okay, we just don't know the temperature at the surface, which is difficult to measure. So let's assume that we know this temperature. We also know what the analytical form of this equation is the Clausius-Clapeyron curve. So we have this slope that is known, let's call it delta, and then we can approximate this difference by its linearized approximation, which is delta times the difference in temperature. If this difference here in temperature is not too big, these two quantities are relatively similar. That's what Penman assumed. With this, then we can write the difference of the two saturated vapor pressures as function of the difference in temperature. If we do that, here is what we get in our system. So we rewrite our system as we had before, and now instead, well, first let's do another simplification here. So let's consider these two equations first. We solve for H so that we eliminate H, and we combine these two equations, and the resulting expression, we express it as a function of T naught minus TA. So we solve for T naught minus TA, and we get rid of sensible heat flux, expressing it as net available energy minus latent heat flux. Okay, so if we have this now, this system is now two equations. You can see that there is T naught minus TA in both. Let's get rid of that, and with a little bit of algebra, not certainly very difficult, you can solve for E and obtain an expression for evaporation. This is the famous Penman equation that is expressed as the sum of two terms. One is related to the available energy and one is related to the VPD. We have introduced here this parameter gamma, which is the psychrometric parameter, psychro, not psycho, which is mostly a function of temperature. It's a thermodynamic quantities, heat capacity at constant pressure here. This is atmospheric standard pressure and the latent heat of vaporization. So the resulting equation is this one that we saw in the previous page. It's usually written slightly in a different way so that one can see give names to the different component. That was done by Penman in 1848, where we have the first term that is called equilibrium evaporation. This is the evaporation that you would have if the VPD were zero. Okay, that's the only the contribution that you would have if the atmosphere was saturated, but there was only a difference in temperature. You can actually have evaporation even if the surrounding air is saturated. Like you can still dry your hair in a very saturated bathroom as long as your hair gets warmer than the surrounding temperature. You can still have evaporation. You will not dry very fast your hair though. The other part is the drying. It's called the drying power of air. People just define this EA as the drying power of air times thermodynamic combination of quantity. Now Penman did this in 1948, had this clever intuition. I believe it was mostly for analytical purposes, mostly because in those times solving the system numerically was not easy, the original system of three equations. For now for us it's very easy to do that, but the approach still has lots of value because it provides this expression here. It really shows us what are the two contributing components to the evaporation, the available energy and the effect of VPD. We will see that when we get to the Priestley-Taylor equation at the end, this structure here will be preserved, and this will be surrogated by a constant. We'll see that later on. What if we have a non-wet surface? This is what Monteith did in 1965 to amend the equation of Penman. So he said, well, I want to do transpiration from a canopy, from a stoma. And the stomates here are unsaturated. So the first thing is we don't have saturated vapor pressure. The second thing that he considered, and he didn't worry too much about the unsaturated part, as we will see. But the second part that is crucial for us is that the pathway now for latent sensible heat flux and latent heat flux are different between the points at which the evaporation takes place, which is inside the stomates. There are two conductances, the stomatal and the atmospheric conductance, as opposed to one only, which is the atmospheric conductance for the sensible heat flux. So we need to keep that into account while we do the combination. That's what Monteith did here. So the usual, the same story, the three equations together, transpiration, sensible heat, and energy balance like before. But now, pay attention here, we don't have a saturated vapor pressure. So first of all, in reality, we have to change the conductancy. So we have the series here of the stomatal and then the atmospheric, and we only have the atmospheric here. And second, as I was saying, the inside vapor pressure is not saturated, but depends on the whole soil-plant-atmosphere continuum. It depends on the temperature, but also on side leaf, or what is the water potential at the leaf level. If we have a drought, definitely this will not be saturated. But then the story is the same. We can have here the VPD appear. We can do the linearization. Now watch out, the linearization cannot be done as easily as before, because the problem is that we don't know where this point is. The functioning point depends on how the plant is. We cannot say it's saturated. So it's certainly on some side here of the vapor part, and this is the liquid part of the Clausius-Clapeyron diagram, but we don't know where it is. Now, if we are in conditions that are well watered, in which inside the stomates the vapor pressure is almost saturated, then we may be in good shape and do a good approximation like we did with Penman. But if it is very dry, we may be in trouble. Well, at any rate, Penman didn't bother about that. Sorry, Monteith didn't bother about this point and just went ahead, combined the two equations as Penman did, and obtained this Penman-Monteith equation. That's how we became famous. So where the evapotranspiration or transpiration at this, in this case through the stomates is given by two terms like before, a potential term related to potential transpiration related to the energy, available energy, and a part related to the drying power of air. Now, if the stomatal conductance tends to 0 here and here, it's easy to see that this equation actually becomes goes back to the Penman equation. How does this equation do in terms of computation? Well, here is a comparison of the results applying Monteith equation compared to the calculations that you would do solving the full system of equations like we did in the previous lecture. So the black points here are the solution that you would get from the soil-plant-atmosphere continuum. This is the solution that you would get from the energy balance, the intersection, which is this star here. I'm going to put the cursor right on top of it. Is the real, let's say, the solution that you get numerically with the full system. And this one instead, the gray circle here is the Penman solution. So not all in all, not a bad approximation. You can see it here. It's basically a slight overestimation. Well, it makes sense. The inside of the stomates, we're assuming it's saturated, so we're assuming that the system is well watered. But what really saves us from big errors is the fact that the stomatal conductance, even if you go to very low value of water potential inside the leaves, the stomates close, and so reduced transpiration, overriding the effect of actually having freely available water inside the stomates, which is really not the case in a plant that is under drought. So that effect really saves the Monteith equation. Now, of course, we need to pay attention, because if we're during a drought and the stomates are not saturated, and for some reason they cannot close because they're starting to be damaged by the drought itself, or because there is cuticular transpiration, which is the transpiration through the leaves, through the leaf skin, the cuticle of the leaves, that is not through the stomates. So there is no control there. The plants cannot close the cuticular part of the transpiration. In which case, Penman would give you a result, and the reality would be different. So watch out with that. Let's get to the central part of this lecture. So we have done the combination approximation. We have seen the structures of the equations. We will use them at the end. But let's switch gear here and consider what happens if we don't know the variables, the quantities just outside, above the canopy. We have assumed in the previous equations that QA, TA were known, the temperature, the specific humidity, also the wind speed, the way we calculated the atmospheric conductance just above the canopy in this phantomatic logarithmic layer that we will describe in a moment. But this point in which we imagine we have a tower, we imagine we have something that measures for us in continuous time throughout the day, QA, TA, the velocity, and so on. And so that we can plug into the equation as the atmospheric, lower atmosphere condition, and then solve the Soil-Plant-Atmosphere Continuum equation. Now, what if we don't have this available? What if we want to model these quantities? We need to add other equations. And what we need to do is to add these equations for the atmospheric boundary layer. We'll do a simplified version of the reality, which is very complicated with lots of turbulence, but it's a simplification that works very well, exactly because of the complication given by turbulence that mixes things very well. So what we will add is to, what we will do is to add the water and energy budget equation of this atmospheric boundary layer, which is so well mixed that is also called the mixed layer. It's called the mixed layer approximation, what we will use. And then we will couple it with the equation of the Soil-Plant-Atmosphere Continuum and the fluxes of water and fluxes of heat, the sensible heat flux. So this boundary layer will be a slab, will be a mixed layer, and now the boundary condition will be above that, which is the free atmosphere. So the condition of the free atmosphere will be our new boundary condition, which is good because they vary more slowly compared to the ABL. And so instead of changing hour by hour or half an hour by half an hour, they change with the synoptic conditions of weather systems, which has a time scale of 1 or 2 days. So during a day, unless we have a very fast front coming, we can really keep them constant and assume a single value during the day. And so, which means that we will have to provide the entrainment fluxes, that what is the energy and water flux at the top of the boundary layer. And once we have done that, then the only input will be the only thing that changes in time is the solar radiation, Q of the net available energy. What is this atmospheric boundary layer? It's something that we normally don't see in a clear day. It's a layer of intense turbulence, intense mixing here, that it goes from the surface above this logarithmic layer. What we have is, this is the wind profile. Let's go step by step. So let's say that the mean wind direction is this one. We have a roughness layer, the canopy layer. Above it, there is a strong gradient in velocity, and this has a typical logarithmic shape, the logarithmic layer. Above that, it's almost constant. This is where there is lots of turbulent mixing. Okay, it's the ABL is the mixed layer. This is the height of the boundary layer of this mixed layer that grows in time, and above that there is an inversion, and on top of that there is the free atmosphere. Now the free atmosphere is typically much less turbulence. This is very turbulent, so that is mixed, well mixed. You don't see it in a cloud-free day, but what you do is you feel it if you fly. If you're flying at this interface, you have turbulence here, almost no turbulence, a potential type of flow in the free atmosphere, and that's where you get the interface here with the bumpy ride at takeoff and landing. That's the typical level at which the height of the boundary layer arrives. Now, during the day, you have radiation coming, net available energy coming. You have latent heat flux going up if there is evaporation or evapotranspiration, and sensible heat flux H. So this is the typical energy partitioning that we have. The atmospheric boundary layer is this mixed layer that grows during the day. So as I said, is the lower part of the troposphere. Tropo means motion in Greek, so is the sphere where there is the most motion of the lower part of this where there is most motion because there is lots of turbulence. Above it, there is the free atmosphere. As I said, it's potential type of flow. The wind is baroclinic, meaning that it's parallel to the isobars in the upper part. The atmospheric boundary layer has a typical diurnal daily evolution. It grows, starts very small during the day. It grows from when it gets enough energy from the sun, and during the warm days, it reaches its peak in the afternoon. Later in the afternoon, it can reach 1, 2, or even more kilometers. It's typically thicker at the tropics and at the equator, and much shallower at higher latitudes. At night, it's a completely different story. It collapses in the evening. There is not enough energy, so it deflates. It deflates like a balloon, and it remains stratified with less turbulence at night. It's very complicated. We'll not deal with the stable nocturnal boundary layer. During the day, as I said, there is intense turbulence. The system is well mixed, so that the profiles of the main variables, humidity and potential temperature, which we will define in a moment, are practically constant throughout this layer, which is a great thing from a modeling point of view, because we don't have to deal with functions of the vertical dimension, but just put constants and have this mixed layer approximation that works quite well. The lower part, as I said, is this logarithmic profile, and that will set the top of the logarithmic profile will set our boundary condition, this interface condition between what happens below that we have studied before, the Soil-Plant-Atmosphere Continuum, and the upper part, which is the atmospheric boundary layer. Now, the logarithmic profile, as I said, requires similarity theory, concepts of turbulence similarity theory that we have not done so far. If you're interested in that, go and see section 2.3, where we also define the atmospheric conductance. We'll see that later on. So between the logarithmic layer, which is a very shallow part on top of the canopy, and the free atmosphere, there is this growing layer, the atmospheric boundary layer, where the main variables, as I said, in this mixed layer have constant profiles, and in particular the velocity, the potential temperature, and the specific humidity. Now, these are unfortunately a little bit tiny figures, but here we have potential temperature normalized with respect to this minimum at the surface, and here is a specific humidity Q. Sorry for the change in notation. This is taken from a paper by Mario Siqueira, Gabi Catul, and myself a few years ago. So specific humidity and potential temperature, which we'll define in a second, have you see, these are sounding profile. These are measurements made by balloon that have been sent in the atmosphere at the Greensboro. Several profiles measured like that at the Greensboro Airport in North Carolina. So there is a portion of the atmosphere up to this point, which is the height of the atmospheric boundary layer, in which the profile is relatively constant. And then there is a sharp change. This is the capping inversion, and then almost a linear increase in potential energy, in potential temperature, and decrease typically in specific humidity. The free atmosphere is usually warmer in terms of potential temperature, not of real temperature. there is a combination of, we will see, of pressure and temperature, and drier in terms of specific humidity. But what is important for us is that this guy is almost constant and this guy is almost constant. So we'll keep them constant throughout this layer that changes in time. So we will have a height of the boundary layer, which is a function of time here, and between a tiny logarithmic layer here, which is exaggerated in comparison, and the free atmosphere, where there are these linear profiles of specific humidity and potential temperature that vary linearly according to this gamma, theta, and gamma q, which are the lapse rates. These are the typical values that you can set that change day by day or every 2 or 3 days, depending on the weather conditions. That this will be our boundary conditions now. These slopes and the intercept here of this function, q naught and theta naught. These are the free atmosphere boundary conditions. Within this layer, instead, theta and q will remain, at least according to our mixed layer approximation, constant. So this function here will change during the day, but will only grow. This layer can get larger. Typically, the potential temperature grows. This can actually be higher or lower depending on the surface condition and the free atmosphere, but it will always remain well mixed and constant. What is potential temperature? The potential temperature is a temperature that you reach at the end of a thermodynamic process of adiabatic compression or expansion. So the temperature is the potential temperature is the temperature that an air parcel would have if you brought it adiabatically from its initial state to the standard atmospheric pressure. So imagine that the standard atmospheric pressure is the one that you have at the surface, and so you take a parcel from higher up in the atmospheric boundary layer and you bring it down to the surface. You need to bring it down relatively fast, as the turbulent vortices in the ABL do, such that there is no time for the parcel to exchange heat with the rest of the environment. And that's what adiabatic means. No flux exchanges of heat with the surrounding. So if that happens, then the new temperature is given by this thermodynamic equation, which is the potential temperature theta is the actual temperature of the parcel that you had at the beginning. P is the original pressure from which you started. P naught is the standard atmospheric pressure, 1 bar. And this exponent is the ideal gas constant for dry air, and Cp is the heat capacity at constant pressure. So this is the new temperature that you'll get at the end. If the pressure was lower, this is going to be than the atmospheric pressure. This is going to be a number greater than 1, and the temperature, in fact, warms up as you compress. If this were an expansion, if you start from a higher pressure than atmospheric pressure, this is a number less than 1, the final temperature is lower. So expansion basically cools down and compression warms. This is only the temperature change due to this expansion and compression, not to heat exchange. So apart from a constant, if you take the log of this theta and you go back to chapter 2, where we saw the entropy expression for an ideal gas, you will see that basically taking the log of this quantity, you'll get the entropy of the dry air, apart from a constant, which means that this adiabatic mixing is also isentropic. There is no change of entropy as this mixing does, because there is no heat exchange. So we can also say that the ABL behaves as isentropically with respect to temperature. The temperature and potential temperature obviously are equal if P is already equal to P naught. So if this is 1, the whole thing is 1, and theta is equal to 1, which means that the temperature and potential temperature are the same value at the surface. So once a surface means canopy or just above the canopy. So the logarithmic layer, in the logarithmic layer, we can assume that TA is equal to theta A, and start from there. And temperature in the ABL will go down as we go up with elevation, of course, cooler air as we go up, but potential temperature will remain constant until we exit from the ABL into the free atmosphere. The approximation of constant variables, of course, we saw that it's well approximated by these sounding measurements that we saw at the Greensboro airport in 2 slides before. But it's also, if you don't like the approximation of mixed layer and you decide to do a top of the line type of calculation, doing turbulence simulation with the so-called large eddy simulation of the atmospheric boundary layer, which is what Stevens has done here in this Journal of Atmospheric Science paper, you will see that after lots of calculation, you will get a profile, and this is potential temperature, which is pretty constant. So the approximation is actually good, and this avoids us all the millions of calculations that you would do otherwise if you had to follow at least the large eddies, not even the small eddies that are impossible to follow, but at least the larger scale turbulence of the ABL. So we are pretty sure that we are doing a decent approximation because of both measurements in the field and this type of simulations. With this approximation of the mixed layer for the ABL, we can write the conservation equations that govern its evolution. We assume that the boundary layer is cloud-free. We will think later of what happens when clouds form in a few slides. But for now, let's write down first the balance of static energy, the energy that is associated with the sensible heat flux input, not the latent heat flux that is input of vapor that also brings its own energy, but doesn't contribute much to the buoyancy and therefore to the growth of the boundary layer. Actually, in our approximation, it contributes 0 to that. So this is the rate of change of the enthalpy of the boundary layer of a slab of height h. Cp times theta, if you remember from our review of thermodynamics, is actually the enthalpy of the perfect gas. This is for a height of the slab h, and Cp is constant, so goes out of the derivative. So we have just the rate of change of potential temperature with respect to time. So the change of enthalpy is equal to the inputs minus the outputs. Where are the inputs or the outputs? At the lower boundary, at the interface with the logarithmic layer, we have the input of energy as sensible heat. So this is the sensible heat flux that we've seen before, H. And the other part can be an input or an output. Typically, it's an input because the free atmosphere is warmer, and it's exactly how much heat in terms of of potential temperature comes from the fact that the boundary layer is growing and encroaching into the free atmosphere. So by encroaching and eating up some of the free atmosphere, it entrains some of its energy too. And how much energy it entrains is the difference between the theta of the free atmosphere, theta F, minus the theta, which is constant in the boundary layer. So this is the jump between at the inversion layer above the ABL times the speed at which the boundary layer grows. So the rate of growth, dH, dt itself. And the rest is just for the dimensional reason to make it an enthalpy. So similarly, for the balance equation for the conservation for water, the water balance equation of the ABL. So the rate of change of how much moisture we have, Q is the specific humidity over a height h in time, changes because of inputs minus outputs. Inputs being at the bottom evaporation, evapotranspiration from the logarithmic layer. That's the evapotranspiration flux that we've discussed so far. And then similarly to the previous equation, we have how much moisture is entrained or lost, depending if the free atmosphere is drier or wetter. Then usually it's drier, but it could be it could be also wetter than the ABL. So we have, as before, the difference between the specific humidity of the free atmosphere minus the specific humidity of the ABL, that's the jump in Q, times the rate of growth of the ABL. That's our second equation. The third equation is the growth equation itself, how fast the boundary layer grows. This is related to how energy input at the surface given by the sensible heat produces buoyancy, turbulence, and then makes the boundary layer grows. The equation is relatively simple, but it comes out of a relatively complicated turbulent kinetic energy closure at the capping inversion. And for that, I'll just take it for granted here. And if you want more information, you should read the paper, the original paper by Tennekis. It's a classic 1973 Journal of Atmospheric Sciences. And the derivation is also repeated maybe more compactly here in my paper in the boundary layer meteorology in 2009. The equation is relatively simple. Is the HDT grows proportionally to the heat flux H, and 1 plus 2 beta. Beta is just a constant, something on the order of 0.4, 0.5, and then divided by stuff that is just thermodynamics, CP. This is the gamma theta is the lapse rate of the free atmosphere, the profile of theta for the free atmosphere, and then divided by the height of the boundary layer. So the higher the boundary layer, the slower the evolution is. So this slows down a little bit the evolution. So altogether, these equations have to be coupled to the lower boundary, which gives the fluxes, as we saw, of latent heat and sensible heat, and those are in turn related to the surface energy balance and the soil-plant-atmosphere continuum. So we can see here the role on the meteorology, on the atmospheric boundary layer, that the soil-plant system has. So we have, if we write down, in fact, specifically the energy balance, as we have done, available energy, sensible heat, and latent heat of evaporation, then we have that H is this usual transport formula that we've seen. So it's now the difference between, remember that at the surface temperature, the pressure is basically atmospheric pressure in the logarithmic layer or in the canopy. There are not huge differences in height to justify differences in pressure. So we can use either potential temperature or real temperature because they're the same. So the theta S is the temperature at the surface minus theta in the boundary layer. This is the driving force for heat times the atmospheric conductance, as usual. So I've just rewritten the previous one in terms of potential temperature. And then the evapotranspiration, which is the gradient of a specific humidity between just outside the surface and the boundary layer. This is at the logarithmic layer, and this is at the surface, and this is in the boundary layer, and plus times the conductance given by the series of stomates and atmosphere. So let's see inside this where the role of the ecohydrological processes of the plants and the soil controls are. We can see certainly in the atmospheric conductance, if you remember, the atmospheric conductance depends on how turbulent the layer above the canopy is, and that depends on how rough the canopy is, which in turn depends on how tall the canopy is. So that part contains the canopy height. Depending on the vegetation, GA will be different. The Q itself is the net, contains the net radiation. So how much actually is reflected away is lost via the albedo fraction. And so that also depends on the type of vegetation we have. Remember, in the previous lecture, we saw that vegetation height also controls how albedo and color, of course, but mostly the height changes how albedo is for vegetation. So that's another strong control of vegetation on the physics of the ABL and the fluxes. And then, of course, the stomatal conductance. This is the most important control. Stomates open and close, plants try to save water, and by doing that, they change the energy partitioning into the ABL, and they change its growth. And we remember that GS may be related to A, A being assimilation, if you use Looning or Norman's model. But in any case, it carries together the stomatal function, the plant functioning, the assimilation, and the photosynthesis. So through GS in here into the flux and then into the energy partition, we see all the variables that come from the plant: the leaf temperature, the leaf water potential, internal CO2 concentration, radiation, and so on. In turn, Psi-L, of course, Psi-L is also contained here in the unsaturated specific humidity inside the stomates. Both of them, both GS that contains Psi-L and QI that contains Psi-L, to get that, you need to backtrack from the leaf level down through the soil-plant-atmosphere continuum into the soil condition. So depending on soil moisture, this will be different, the fluxes will be different, will change the partitioning, and that will affect the growth of the boundary layer. So that's a neat way to see the connection from the surface into the atmosphere and how the land interacts with the atmospheric dynamics. Putting all these equations together, the equations of the atmospheric boundary layer, the dynamical systems that we wrote of 3 differential equations, plus the energy balance at the surface, plus the soil-plant-atmosphere continuum, all the equations for the conductances, all the way down to the soil. If we know what's happening in the soil moisture, and if we happen what happens at the top condition, which is the free atmosphere, which vary very smoothly, very, very slowly, we can now solve the system. We need to provide, of course, a temporal behavior for the input of radiation, but that's if you don't have clouds, that's pretty much like a parabola that starts at sunrise, peaks at midday, and goes down to 0 at sunset. Then you can do simulations. Here it's a simulation of 7 days of clear sky during a dry down done by Edoardo Dali et al. In 2004. And what we can see here is that, okay, during the night, we just close the stomates, nothing happened. We assume that there is basically no transpiration, soil moisture is constant. But during the day, soil moisture goes down, and these are the subsequent days, how much you lose moisture. And notice that these steps are smooth and become smaller and smaller because you tend to lose less and less as you keep going. And these are the main variables of the soil-plant-atmosphere continuum. These are soil water potential and leaf water potential. You can see the soil goes down slowly, connected by the retention curve through this value here of soil moisture. And during the day, leaves, actually, when they open, at the leaf level, the flux brings down the water potential. So you'll get a minimum here, and then as the stomates tend to close again, the leaf water potential goes up, and then the next they go even further down and down and down. As the soil dries, the flux provides more resistance, the leaf gets drier and drier. You see that at the end of the 7th day, you'll have already something in the middle of the day. The minimum is around -3 megapascal. The continuous line is using using Jarvis formulation, and the dashed line is using Looning Norman formulation. So embedding also the information of photosynthesis is a more complicated system to solve. We just wanted to show here the comparison between the two. But apart from a few changes at midday, the general trend is the same. And you see that here you have D is the specific humidity deficit, so maximum during the day at midday here, but increasing as the soil dries. In the simulation, we let the soil dry, but we kept the free atmosphere conditions the same for 7 days. It's not very, well, it may be realistic. It's not common to have for 7 days exactly the same conditions, but it's to keep constant some of the variables and see the impact of the dry down of soil moisture. So you'll see that depending on the two formulation of stomatal functioning, then also the VPD, the vapor pressure deficit inside the stomates is, and the atmosphere is different as the drought progresses. This is a stomatal conductance, so open, very conductive, well water conditions, slight difference between the two models, but pretty much the same. And then you see that at some point here you start seeing, especially in the looning model, which is more sensitive, is connected to the whole photosynthesis model, the closing, the drop at midday. We will see it better in the next slides where this is magnified. Evapotranspiration, same thing, well water condition, not very low in the morning, 0 actually, maximum midday, and so on, until, at least for one of the two models, you get midday stomatal closure because of water stress and therefore drop in evapotranspiration. The Jarvis model here has not yet produced any reduction at midday of evapotranspiration, whereas this is net assimilation. In the net assimilation, both models have at some point a reduction at midday, more pronounced for the looning Norman model you see at midday here, but both of them have this drop at midday because of stomatal closure. Of course, Jarvis can be solved independently of the photosynthesis model, and then the photosynthesis model can just be run offline with the values provided by the environmental quantities provided by the solution of the Soil-Plant-Atmosphere Continuum and ABL coupled together. The looning Norman model has to be done all together. The nice thing is that with this type of model, complicated but really as simple as it gets at this point, with mixed layer variables and compartments in the Soil-Plant-Atmosphere Continuum, you can get good approximation of the observations that one would measure in the field. Yeah, these are the days, the 12 consecutive days that we saw at the beginning of the lecture, of the previous lecture, not this one, that were measured at the Duke Forest, and you can see that the trends are generally well reproduced. If we look at things in more detail, this is just one day, so these are 4 days superimposed on each other. We start at the beginning in well water condition and then progressive. These are 4 days of progressive drying. This is at the maximum, at the final day of the simulation. We had no rain, so we let it run as if there was no rain. We can see a little bit better the trend. So stomatal conductance and comparison between Jarvis and Norman, the Norman looning model. So stomatal conductance, it opens up at the beginning. This is sunrise, stomachs fully open, try to take advantage as much as they can, and then during the day, especially when it gets drier and drier in the subsequent days, at midday they tend to close to avoid extra losses and too much stress. In fact, the Norman looning does it even more than Jarvis. The behavior is the same, but you see that the closure is even more dramatic. This is, you can see the repercussion of stomatal closure in transpiration at the beginning maximum when you have well water condition, and as the soil dries, you see that the peak is reduced. The stomachs begin to close for at least the central part of the day, and the curve flattens and even gets depressed with almost like a bump, almost like a minimum here, not quite, but almost for the other model. But all in all, again, pretty similar result. And finally, assimilation, where you see a similar trend, but because of the extra constraints, environmental constraints on assimilation, on photosynthesis, you see even more dramatic with the real minimum here for the looning, for both Jarvis and the Looning model at need date. And when you see that at day 7, when you have complete almost closure of the stomates here and here almost complete closure of the stomach, assimilation, of course, is also impaired as it is with with transpiration. So all in all, nice results, but lots of equations coupled together, each of them communicating with the other with interesting feedback that we have learned to appreciate and understand. At this point, in front of this simulation, it's good to go back, and that will be also one of the problems at the end. Write down all the equation, understand how the variable talk to each other. Can we do something beyond numerical simulation? Maybe we can do some analytical consideration that will help us see a little bit of a structure of how the variables can simplify and learn a little bit more of this interaction. So we will stick to well water condition to keep things simple and not have to deal with the stomatal closure and stuff like that. So what we'll do in well water condition is simply having the equation of the boundary layer here, the energy equation, the water equation, the growth, plus the energy balance at the surface, available energy, latent heat, and sensible, the usual. Now this is algebraic, but these are three ordinary differential equations, so a system of 3 ODEs that forms a dynamical system. The best way to study it is to go in the phase space. What was the great intuition of Henri Poincaré, the French mathematician, who said these equations, this type of systems, are better studied in geometrical forms. And so this article by Nolte is interesting. It gives you a little bit of the story of the phase space, and also in section 2.4 of the notes, there is a bit of review, as we saw, of dynamical systems. But the story is that you are in 3 dimensions. The phase space has 3 dimensions: theta, q, and h. So it's and as you solve it in time, imagine that you solve numerically this system. As you solve it in time, the point q, that is q, theta, and h, moves in time and describes an object, and that object is the trajectory of the system, and it lives in 3 dimensions. But in reality, what we'll see in a moment is that that object is almost 1 dimension. It's very much a projection that lives on a simpler space. If we can understand that geometry on that projection, we can get simpler expression. So the first step to do here is to realize that by combining 2 equations, we can see that apart from some initial condition that we can forget about, the end result is that theta is this theta tilde approximated is linearly related to the height of the boundary layer. So there is a one-to-one connection: higher boundary layer, higher potential temperature; lower boundary layer, less potential temperature. The rest here is just a constant, and it depends on that beta, which is, let's say, 0.5, the factor of the closure of turbulence at the top of the ABL, and gamma theta, which is the lapse rate of the free atmosphere. So nothing that changes in time. How can we see this? Well, just very briefly, let's combine these 2 equations. So the way it goes is that we eliminate H, the capital H, the sensible heat flux, from these 2 equations. So let's solve this H. So let's take this guy on the other side and bring it here. So you will see that you'll have 3 terms inside this first equation that have d theta dt. They have something that is dh dt times h, which is dh squared dt times 1/2 here. And then we have dh dt. So something at the end that can be immediately integrated in time and solved once for all to obtain this equation. It's not a difficult calculation to do. Try it by yourself. And so that means that things here are pretty simple. Theta and h are directly related. We can play a similar type of game that doesn't give us simple result as the previous one, but still reveals something. And we can actually substitute first for E this guy here. So we solve this for E, we plug it in here, we get Q, we get minus H, and then for H, we substitute again this. So again, we will have three terms that are time derivatives that can be formally integrated at least once to provide an approximated specific humidity Q that depends on many terms. You see that H remains, there is so it's linear here with H, but here we have 1 over H, so it's nonlinear with H, this term. Plus there is a term which is the integral of how much energy you got until time t hitting the surface. So this is actually a memory term that makes the specific humidity much more complicated and interesting if you want than the potential temperature. So the height of the boundary layer doesn't define the specific humidity. The specific humidity is defined by both the height of the boundary layer at a certain time and by the history of how much energy has been accumulated throughout the day. You can actually now take these two quantities and plug them here into, well, you write the full expression of the sensible heat flux with these values here and the partitioning, and long story short, you can write a single equation for the HDT, which is complicated. It contains H here as in 1 over H. It contains H here, and again 1 over H here again. So it's a nonlinear differential equation in H, plus a temporal term, so it's non-autonomous. And again, there is this term related to the memory, which comes from the moisture part, as we've seen before. So the growth of the boundary layer depends on how the state at the moment is, non-linearly on that, H of t, and it contains the full history itself. So the way at some moment during the day it grows is related to how much energy it has accumulated since sunrise. So that's an interesting piece of information that these analytical manipulations allow us to see. But can we do something more? The structure of the equation, if you look at the previous equation that we wrote, and we just compact symbolically all the terms, it's an ordinary differential equation with nonlinear dependence that has a term that depends on 1 over H. The variable is H, okay? The height of the boundary layer. And then one term that contains H squared plus a constant. And this F of t and G of t are time-dependent terms that depend on the temporal variability of the force in the input, the solar input that is maximum at midday and 0 at sunrise and sunset. If you do the simulation, the full simulation, and you study this term, something that my former student J.R. Rigby and Jun Yin have done in a paper with me a few years ago, you realize that these two guys here are actually compensating each other in time, and they're almost constant. So you can rewrite the whole business as the HDT, not exactly the same, but almost well approximated by the HDT, a function of t, which we'll see in a moment is just something known, divided by H, plus a constant. Now this looks like a pretty simple ordinary differential equation, and that's what we thought originally before studying it, and JR was pretty happy to have found this approximation until he realized that this is an ABL equation of the second kind. And Abel was a pretty good mathematician, and he told us that he was not able to solve it. And actually, it turns out that this it's only solvable in very special cases and not in this general case. No, Abel was this great Norwegian mathematician. Look at the poor guy died. He was not even 28, but was such a good mathematician that the other French mathematician Hermite talked about him very highly, and he said Abel has left mathematician enough to keep them busy for 500 years. In these few years of his life, he discovered so much and raised so many interesting questions. Well, certainly it kept JR busy enough for a while until we realized that we had to resort to different types of simulations for different types of approximations to solve this equation. So what we ended up doing is to just see how things were going is first to realize that C prime here is a constant, but changes if you want to change the VPD of the atmosphere. So it's sensitive to that. And second, we cannot solve this fully exactly, but we can do a perturbation analysis, assuming that this is not a big quantity compared to the rest. And so we do a first solution, a first order approximation in which this is considered zero. And this is solvable now. This is just separation of variables. dH dt equals a function of t over h. You take h on this side, you rewrite it as 1/2 dH squared over dt, and this can be integrated symbolically as a function of time. So that's what we did here. You get, and you call this equilibrium solution for the first order solution, and then you add small variations to that. So the final solution that we got is this h bar as a function of t, which is the h equilibrium, the one that you would obtain by taking C prime equal to 0, which is this solution. As I told you, it's just twice the integral of f of t dt, square root, because you had the h square on this side. So just separation of variables, plus the correction that you would do at time variability times C prime. C prime, you know, and t. And actually this surprisingly works well. This is just the shape of what you have in f of t, which is a function of the equilibrium Bowen ratio. The time variability comes from the net energy input Q of t. Sometimes we call it Qn, sometimes Q, sorry about that. But this is the net input of energy at the surface. And the equilibrium Bowen ratio just contains thermodynamic stuff, the slope of the Clausius-Clapeyron curve, and things like that. So when we look at the simulation, if you do the whole simulation of the system during a day, so this is sunrise, this is sunset, and this is the height of the boundary layer. So we imagine that we start from very small values, almost 0. The boundary layer grows. This is an approximation that doesn't work very well. It's this H equilibrium T. But the full solution is this M1, the blue one. And this is the correction. This is the approximation here, H bar. And you see that it actually does a very reasonable job in much simpler terms. And we can actually follow its evolution in time. So after 4 hours, let's say here we are midday, so we are already at almost at 1,000 meters, and then you see the tapering off of the growth. In this case, the maximum height is reached at sunset, when then the boundary layer has no more energy and collapses. And we are at about 1,100 meters or something like that. So interesting results with the structure of the equation that contains this memory term that we could disentangle by doing these substitutions. But so far, we've seen the boundary layer growing as if we had no vapor in it. The only role of the water vapor was to partition the incoming energy into evaporation and sensible heat. And we were just pumping the sensible heat into the equation and making everything grow based on that. At some point, if the boundary layer is wet enough and it grows fast enough to higher elevation where the real temperature, not the potential temperature, but the real temperature is colder, there could be a level at which you start having condensation. And we can notice that many times looking at in the afternoon at clouds during a formerly nice day, you can see this lower level, the bottom of the clouds tend to be flat. This is the so-called lifting condensation level. This is the level at which, if the boundary layer, so this is the boundary layer, no? And let's say that this is the height of the boundary layer. Now this is a convective cloud, a cumulus that has already been developed into deep convection. But let's assume that before that, when you have just the fair weather clouds, small clouds here with a flat bottom. So what happens is that the boundary layer grows, this level here keeps going up, and at some point it reaches this it may reach the lifting condensation level. If that happens, at that point, if the boundary layer keeps growing, but from that point on, the air inside becomes condenses and forms clouds. And so from this point on, you'll get the little cloud here with the flat bone. The boundary layer keeps growing. At some point, these clouds start developing if the conditions are right. You have the, as I was saying, deep convection, and at this point, the boundary layer approximation, the well-mixed approximation, just goes belly up, and you cannot use it anymore. But up to that point, it's a good approximation. Then you need to adjust it to cloud top boundary layer and do more acrobatics, and things get more and more complicated. But let's try to see what conditions lead to this and what happens as we get there. And this will tell us, this will allow us to study how the growth of the boundary layer, which in turn depends on the soil plant system, then affects the potential for free convection, for deep convection, and potentially then also development of these big towering clouds and convective precipitation. So this was an analysis done by Jun Yin and John Albertson in a WRR paper a few years ago. So the starting point is to consider the moist adiabatic process. No, we define the potential temperature as that temperature that you would get lifting or lowering, but meaning compressing or expanding adiabatically a dry air parcel. Now let's suppose that this air parcel is not dry but contains water vapor. So as you take this air parcel plus water vapor and you move it up and down adiabatically in the atmosphere, adiabatically meaning fast enough that it doesn't exchange heat, and so it only changes temperature because it expands and contracts. At some point, it may actually, as it goes up, it cools, the water vapor can actually condense. And condensation is associated to a release of heat. And exactly the opposite what is associated with evaporation. You need to provide heat to allow some vapor to liquid water to evaporate. In this case, if vapor condenses, it will release heat into the rest of the environment, into the surrounding air. So let's imagine that now this is potential temperature. It actually is better to use the so-called virtual potential temperature, which is a correction of the potential temperature theta, but by taking into account of the buoyancy effect, so the content related to the specific humidity Q, to the presence of the water vapor. So but the story is the same. So let's imagine that we are here. This is the boundary layer. So you see the height of the boundary layer, and then there is the capping inversion, and here is the free atmosphere. And let's do the following thought experiment. Take a parcel of air, like where the cursor is here, and lift it adiabatically up here. If you only lift it by that amount, as I've done here in the figure, it stays below the lifting condensation level, which is this ZLCL. If you stay below that, there is no condensation happening. But if you bring it above here, it may release a little bit of heat because it starts condensing. Now from here on, it will start releasing heat. So the potential temperature will be higher than the one that you would have if the air was dry and you were doing things still adiabatically but with no condensation. So this is potential temperature remaining constant with no condensation. It just cools down, but the potential temperature stays the same. In this case here, from here you have condensation, so the virtual temperature starts increasing. And in this part, it is higher than what you would have if the air was dry, but is not higher than the corresponding value of the free energy, of the free atmosphere. So you see here, at the end of the adiabatic lifting, the air is colder than the moist air is colder than what you would have in the surrounding free atmosphere. So being colder, it's heavier and it's not buoyant. And so this is not conducive to further buoyancy and therefore to convection. That's why it's called, the area of this curve here, without getting into the details, is called convective inhibition energy, because of this, because the convection is inhibited here. But if at some point you see this curve cross, and from this point, which is called the level of free convection, if you were to take the parcel here and lift it to this level, now the corresponding temperature would be this one, which is warmer than this value, which is the corresponding value of the free atmosphere. So now you have lifted an air parcel, this has condensed, released heat, and the air surrounding has become warmer and now tends to further go up by itself, because it's become buoyant, it's become warmer. And so the tendency here from this point to this point, which is the level of neutral buoyancy, is that any point here tends to by itself go up to higher levels. The total area under this curve gives a sense of what is the tendency to develop potential convective deep convection. So it's called CAPE, convective available potential energy. This is the point at which this is maximum. Above this point, if you lift it, if you take from here and you lift it here, you're actually again colder, and at this point will tend to fall down this way. Now, of course, these are all thought experiments. The one that really the mechanism that does the lifting and the mixing is turbulence, so that there will be, imagine turbulent vortices that shoot air particles up. If they reach here, they will be negatively buoyant and tend to go back. But if by any chance they pass this level, because there is strong mixing and strong energy that takes us here, once we are here, it's warmer and they tend to keep going up. So the picture is actually the one that I've sketched here. If you now invert the axis, now the z-axis vertical is here on the horizontal, you have the level of free convection and the level of neutral buoyancy. This is the ABL area. If you lift a moist air parcel only on this side, it will tend, it's almost as if you had a potential landscape created by these two quantities, one that is inhibiting and one that is favoring convection, so that favoring further growth. So if the vortex sends the air parcel here below the free convection, it will actually tend to fall down again and stay stable. But if the vortex is strong enough and sends the particle here past the level of free convection, then there is this warmer condition provided by condensation, and the particle tends to rise further and keep going until it reaches the level of neutral buoyancies, at which it doesn't have any more tendency to grow and it will stay here. So in this area, things tend to provide, and don't forget that from here on, as this deep convection sets in, the boundary layer approximation is kind of gone, and this remains just an approximation. So what actually happens beyond this, there are inertia effects, and it could actually overshoot and really get to very high levels. Some towering afternoon thunderstorm cloud can reach way above the troposphere, can go beyond the troposphere, typically 10 kilometers, but some of them can get 12 to 14 kilometers. So that's what you see in the deep convection in the afternoons. The situation is pretty interesting then. It becomes a matter of letting the equations evolve, the boundary layer grow, and tracking whether the boundary layer height at some point reaches the level of the lifting condensation level. At that point, you have the first cloud formation. You see at what time that happens, And also we also want to take stock of what is the level of CAPE at that point. What is the area between the moist adiabat and the free atmosphere potential temperature, so that you can actually get a sense of how much CAPE you have available, how much potential energy for deep convection you have. Some study that's shown that if you pass a certain threshold of CAPE, it's much more likely to have deep convection than the formation of convective precipitation. So this is a simulation done by Yin again, where he considered, here this cursor, okay, so he considered typical values of the free atmosphere. Okay, you have the lapse rates, gamma theta, gamma q, and so on, the maximum radiation at midday of 490 watts per square meter. And in terms of soil plant system, he considered a typical C3 plant in two conditions: one drier soil and one in wetter soil conditions. And then he let the system of those equations that we saw before, this is all numerical solution, in time, evolving time, tracking the height of the boundary layer as it grows, starting from an initial condition here. This is, instead of height, he plotted pressure, but the two are related, of course. So imagine that this is the height and this is potential temperature. And so you see that this is the original potential temperature. This is the initial condition for the growth of the boundary layer, and this is the free atmosphere profile. It's not straight simply because this is pressure, is not height, but he assumed linear profiles with this lapse rate gamma theta. Okay, let's see the simulation and then comment. So you see that the boundary layer grows from the beginning, and at some point it reaches the level of free convection. This happens at different times for dry soil and wet soil. We have that the wet soil has reached it later. The dry soil has reached it slightly earlier, like at noon. But the difference is that there is much more CAPE in the moisture condition. So it all depends on timing, but also amount of energy. You can study the different combination of this simulation depending on the parameters, which is something that we did later on. So it's clear that if at some point you reach the lifting condensation level and you have enough energy, it's very likely that later you will have convective precipitation. These are actually measurements that show that how the conditions at the surface, the Soil-Plant-Atmosphere Continuum, influences the ABL growth, and in turn may trigger convective rainfall. So this is summer day of 2004 over the Duke Forest in North Carolina, where Jenny Wang and Gabi Katul and colleagues have measured and reconstructed the growth of the lifting condensation level during the day. So this is sunrise and this is noon. So you see that the lifting condensation level is higher, but at some point in the afternoon it tends to go down, and instead ML stands for mixed layer. So this is the height of the boundary layer, grows, and at this point, at around 2:30, 3 o'clock in the afternoon, there is the crossing of the lifting condensation level. Potentially first clouds forming, if there is enough CAPE, which was the case in this day. Deep convection, which at this point goes very fast, and you see that after half an hour or an hour that the crossing has happened, you get rainfall recorded at the rain gauges down at the forest. So a nice big convective storm in the middle of the afternoon. Now, this is really touching with your hands, seeing with your eyes the full sequence from the soil, the vegetation, the ABL growth, and the feedback on the rainfall and the atmospheric dynamics. Going back to the work of June, we can put together a more comprehensive categorization of the regimes that lead to deep convection based on the growth of the boundary layer and related to the soil plant conditions. So we have diagrams here showing the crossing time, hours after sunrise, parameterized here. This is no crossing, and this is crossing 4 hours, 7 hours, 10 hours after sunrise. And this is the level of CAPE. So not enough CAPE, and this is CAPE above a threshold of 1,000, 2,000, 3,000, and higher. So what these 2D plots are characterized by are different values in the X and Y axis of the lapse rate of the free atmosphere. By changing gamma theta, we change the stability of the atmosphere. We make more and more unstable the atmosphere going this way. And by changing the gamma Q, this way we're making more and more the free atmosphere humid. So as the boundary layer grows, it entrains more moisture. The 4 regimes that June obtained are categorized here as regime 1. There is crossing, there is no crossing, it happens late, basically it doesn't happen, and there is not enough CAPE. This is yes 2, there is crossing, but there is not enough CAPE. In regime 3, there is not enough CAPE, although there is crossing. In regime 4, both conditions are present. There is crossing before of the level of lifting condensation level before the end of the day, and there is enough CAPE to potentially trigger convection. So the regimes are these 4. These are for well water conditions. Let's see what happens in case, let's put it here, in case of reduction of soil moisture content. There is an animation here. Let's see if it plays. We have the same regime. Now we are talking about soil moisture here at 0.45. That was well water condition. Let's see what happens as we start the animation and soil moisture goes down, how these regimes change. You can see they evolve, they change, and at the end, when it's drier, there is less CAPE in general, but there is a bigger region for crossing of the level of free convection. So you can still have triggering of deep convection, but the probabilities are different and the conditions are related to how the whole system combined together works. Now, with this type of system, we can actually start asking ourselves interesting questions. For example, what if we change the conditions at the surface, but larger scale changes like the ones that are taking place for agriculture? What if, for example, in this part here of Brazil, where this picture refers to, we take the Atlantic forest, which is a mixture of tall forest of C3 type of trees, and substitute it with extensive cultivations of sugarcane, which is a C4 plant? Or what if in other parts of the world we're taking expansive areas of forest or prairies and cultivating them now with corn, which is a fast-growing, thirsty type of plant, which has C4 photosynthesis. Similarly, another C4 plant is the sunflower, which is also cultivated extensively in different areas. So what if we now change, like in this case, type of photosynthesis, but other properties of the soil plant system? How does that have repercussion into the atmospheric dynamic of the boundary layer? This is a set of simulation that June has done. We have time and we have different levels of soil moisture. And the difference, well, here is the growth of the boundary layer. You can see that, and this is, I believe, CAPE. Okay, in the units are different. So this is the growth of the boundary layer. This is the, oh no, sorry, this is the level of lifting condensation level, apologies. And when the two meet, there is the first cloud formation. So you can see that there are not huge differences, but in this case, the C4 plant grows to higher level of at the moment of the crossing of the lifting condensation level. And that time of crossing is slightly different. We're probably talking about 20 minutes here, but it's consistently different between the two types of plants, of land cover. So enough to potentially create a difference in the statistics of rainfall, in the statistics of convective precipitation that we may observe in an area, and clearly showing us that there is a potential for these changes. Now, this is particularly evident at low soil moisture values. If there is more moisture, the two things tend to be closer to each other. Now, this is CAPE, less CAPE, but considerably more CAPE in the case of C3 plants, and and here for well water condition, the two things are more similar. Well, all in all, the bottom line is that changing the soil plant properties has a direct impact on the growth of the boundary layer, which in turn has a feedback on how it rains, which in turn further affects vegetation, and the whole loop of the land atmosphere feedback is then closed and better understood. The last part now of this long lecture is to integrate the diurnal behavior that we have seen together. So we have, let's go back to the original boundary layer Soil-Plant-Atmosphere Continuum model without clouds that we have developed and integrated in time. So these are the diagrams that we saw before from our simulation. And we see that there is lots of temporal detail. There is the, let's see here, transpiration, the start of transpiration, maximum transpiration, closure, and so on and all. All in all, this is lots of detail that may not be necessary if we are running a model that is intended to work at long time scales. If we want to see what are the statistics of evapotranspiration, for example, over many years during a growing season, we may not want to know all the details of when these little changes happen. Maybe what we really just want to have is an idea of the average value during the day. And if we know how much water we lose, or how much carbon we gain, or how much soil moisture, how fast soil moisture goes down day by day, then may be enough for us to run this longer term simulation, saving lots of time, but also allowing us simpler description that in turn then permit us to get a clearer understanding of what's going on and how the variables interact with each other. So what we are going to do next is just to see if we can come up with simple, and the trends actually show that this may be possible, the trends of integrating these quantities, how much the total flux is over a day, and compare them to the amount of moisture that we have. So this was done here by Edoardo Dali in his 2004 paper, where he basically plotted during the dry down that was simulated in the previous slide, soil moisture now integrated continuously over a window of 1 day, how it goes down smoothly. So you don't see anymore the step sort of change between day and night, but still the same behavior of decay, faster at the beginning, starting from 1, there is the leakage part. And then when the leakage percolation tends to taper off, now you have almost constant linear drop here, which is related to constant evapotranspiration. And then at this point here, the stomates are really beginning to close and there is less and less transpiration. This is for the two models, Jarvis and Looning. And next, what he did was quite interesting, is to take, for this soil moisture, now plotted here in the x-axis, and plotting the corresponding value of daily average evapotranspiration. So the total evapotranspiration during a day, and refer it to soil moisture. So we have here very well water condition in which you have a certain value, almost constant, of evapotranspiration, and that value stays almost constant until it starts dropping because of stomatal closure as the soil moisture goes down. So time here is just a parameter here that follows my cursor. So the function of evapotranspiration as a function of soil moisture is pretty regular, a plateau, an almost linear decay, and then going down very quickly to 0 once the stomates are almost all closed. So we can actually, and these are the two models, Jarvis and Looning Norman model. We can actually approximate, if we are interested, and this will be very useful later on for the stochastic soil moisture model, these behaviors by a constant up to a point when the stomachs begin to close, when we start having the first drop, and we call this S star, the onset of stomatal closure or onset of stress, a linear drop up to a point which we call wilting point, where the stomachs are almost basically closed, and then keeping it zero here. This will allow us for a nice piecewise representation of these fluxes that we will use in the daily timescale description. The same story for net assimilation. If you consider the total assimilation of CO2 during a day, you will see that it's almost a plateau at soil moisture up to a point where the stomachs are closed. This S star here is very similar to this one, so we can actually use them. These are the same values, linear decay, and then up to the wilting point, and then zero. The water use efficiency, if you will, is basically the ratio of assimilation versus evapotranspiration, so how much carbon is gained per water lost, and the ratio is almost a constant here because this is almost a straight line, and for both models. So it gives us another measure of efficiency of the photosynthesis versus water use. The really important thing that we need to take home from this slide is that at the end of all the interesting interactions and complications of the soil plant system, ABL growth, and so on, the most important things that emerges is this modulation of the fluxes of carbon and of water, of evapotranspiration, and therefore also of energy as a function of soil moisture. With this behavior here of evapotranspiration at the daily level, sometimes we will use an overbar just to remind ourselves of the daily level, as a function of a maximum value Emax modulated by a function of soil moisture. Function of soil moisture which could be smooth, if that is what we need, or a good approximation is this piecewise function. Okay, so Emax will be our plateau parameter that we will, the maximum evapotranspiration that we get in wet water condition. What is the control of Emax? Well, let's go back to the first part of this lecture. We have seen that in the Penman equation, which is, and in the Monteith equation, which is valid in well water condition, the functional form of evapotranspiration during the day, this equation is valid not at the daily level, but at the scale where you have integrated just the turbulent fluctuation, so like let's say every 15 minutes or 20 minutes time scale, is divided into, is separated in two components. One which is the potential evapotranspiration, and one is the in this part that is related to the drying power of air, the VPD. Now, this is a nice structure which was actually exploited by Priestley-Taylor in a famous formula of hydrology that showed us that when you integrate this over the daily level and you study the mean evapotranspiration in well water condition, and let's say that this is our Emax, the well water condition of transpiration, you can actually say that this guy here, average over the day, is just a fraction of the potential transpiration, which is this guy, and that fraction is around 25%. So when you put them together, you get alpha, which is 126, 125, then with lots of variability, times the potential evapotranspiration that of Penman. So the nice formula here is that the Priestley-Taylor equation is an alpha 125, 126, the traditional value, but in reality a constant that well, not a constant, but something that depends on the VPD. Drier airs will evaporate more, and so we will go to even 1.7, or wetter conditions that will evaporate less. So a fraction in any case of the potential evapotranspiration. This part here is just a moderately increasing function of temperature, so it's something that we can compute from thermodynamics. So we have a nice formula that relates how much input of radiation we have to the transpiration and the structure is related to the combination approach of Penman. In summary, when we will deal with our daily timescale description of evapotranspiration, we will write the average daily rates of transpiration as a modulating function Fs of Emax, as we said, and if we want, we can relate them to radiation in this way. This is also confirmed by independent, these are not simulation, but these are measurements by Federer et al. In a famous paper in WRR in 1979, where they measured evapotranspiration of a forest stand in New England, and they plotted normalized evapotranspiration as a function of soil moisture. This is percentage water content, so 40% relative soil moisture, and you see that there is a kind of a behavior like the one we saw in the integration at the daily level of the simulations. Almost a plateau up to a point where there is a more sudden drop, almost linear, and then almost to zero. So even then, even they suggest a piecewise linear approximation going up to a point where we can say that there is an S star and then a plateau at Emax. So all in all, a modulating function f of s of this type, 1 above S star, linear decay between S wilting and S star, and 0 or almost 0 below S wilting, is a good approximation that we will use later on. A similar behavior can be used for a net assimilation, piecewise, same way, up to S star and 0 at S wilting. And let's not forget that this formula, all our treatments so far, refers to flat terrain. When you have topography, things become interesting, of course, as always, but more complicated. You need certainly to think of corrections that account for slope and aspect, but also if you start having hills, let alone topography, then there is the boundary layer gets disrupted, the meteorology changes, the atmosphere changes because the boundary conditions becomes very irregular, and so there are issues of orographic precipitation and lots of other things that are very difficult to model and that are certainly beyond the scope of our course here. So to conclude, now we can get ready to open the second part of the course, in which we will study the soil moisture balance equation at the daily level, which I've written here in a redacted and a simplified way. So we have NZR, porosity, routing depth, dSTT. This is the rate of change of relative soil moisture. If there is no rain, this is dominated by losses of evapotranspiration and percolation. And we have seen the simulations that Eduardo has done. Basically, we can just write a differential equation that describes this evolution of soil moisture in time. And if you don't have rainfall, it will be a long dry down, beginning very fast because of percolation, and then less fast because of evapotranspiration. And then once the evapotranspiration gets almost to zero, it's a very slow decay with the little remaining evaporation after the wilting point has passed. This behavior here is connected to a evapotranspiration function, which could be smooth or it could be piecewise of this type. A plateau here, constant evaporation at the beginning here, and then this linear drop here that reduces exponentially soil moisture. And then once you get to this point here, you have a very low losses. Leaching at this point is basically zero. See, this is more or less the level of field capacity, but going back to this point, it's tapered off almost to nothing, and it stays there until the next rainfall that will make the soil moisture jump. So one of the exercises at the end as a problem will be simplifying this behavior as a piecewise function, plug it in here and solve the differential equation and see what type of behavior you get here and what are the timing for the different crossing of the thresholds associated. So in summary, a long lecture that concludes the part 1 of the course, the deterministic part. We'll get ready to the stochastic theory next, which first has seen the approximation of the combination approach of Penman and Monteith, and then that has provided the structure for a nice transpiration formula of Priestley-Taylor at the daily level that has given us the evapotranspiration in well water conditions, the one that we called Emax. In the central part, the long part of the lecture, we have developed the equations for the mixed layer, well-mixed boundary layer dynamics, which forms a nice dynamical system that evolves coupled to the Soil-Plant-Atmosphere Continuum coupled at the logarithmic layer and on top with the free atmosphere. So if you know the soil condition, if you know the free atmospheric condition, you can solve for all the quantities inside the soil plant system and the ABL to provide the diurnal evolution during a day of evapotranspiration, assimilation, of stomatal closure, and so on. And finally, if you study how this boundary layer grows towards conditions of convection, you can of condensation, you can actually get a decent sense of how the surface condition affects the probability of getting to the level of lifting condensation level, perhaps with enough convective available potential energy, the CAPE, that may induce convective precipitation. So here is some homework for you, a few problems taken from the notes, and notes with interesting further readings at the end of the chapter. Thank you.